In order to determine whether the relation is a function, we look at the set of inputs. So for number 1 here, the different inputs, -1, 2, 5, 8, and 10. We don't have any repeated inputs, so therefore that is a function. If we compare that though to number 2 here, we can see right away the -8 goes to 2 and -8 goes to 8. So for that one input, then it goes to more than one output. So this is not a function. I guess I never wrote that down for the first one either, but number 1 is a function. Number 2 is not a function. Moving on to number 3, we're actually looking to determine whether the relation defines y as a function of x and determine the domain. So looking at this one, y is a function of x, and really just determining the domain is the question. And again, this one's already solved for y. We don't have a plus or minus in front of the square root. So yes, it's a function, because for any value of x there's only going to be one value of y, at most one value of y. Because the 7x minus 3 is in the square root, we cannot square root any negative values. So 7x minus 3 has to be greater than or equal to 0. And I should actually say that we cannot square root a negative value and get a real number answer. So we just solve this inequality. We'll add 3 to both sides. We get 7x is greater than or equal to 3, divide both sides by 7, and we find x is greater than or equal to 3/7. So again, on this one, yes, it is a function. You'd want to write that down somewhere. And then we'll write the domain in function notation. So I've got x is greater than or equal to 3/7. So that in function notation, we start with the bracket because it has the equal to, so it's starting at 3/7 and going up to infinity. And of course, infinities always have the parenthesis. We have a different problem with number 4. Same idea, determine whether or not it is a function. So yes, this one is a function. Again, we don't have y equals a plus or minus anything, so for any value of x there is at most one value for y. The problem we run into here is 5 divided by 0 is undefined. So that is not a real number. So the question is, what makes x plus 13 equal to 0? And we can solve that pretty easily. Just subtract the 13 from both sides. We get x equals -13. So then the domain for this in interval notation is a little bit long. We get -infinity to -13. And then we union that with -13 to infinity. So we're really looking at -infinity to infinity, just not the -13. So that's how we describe that. And again, yes, it is a function, and then state the domain. For this next one, we want to find f of 3. So all we do there is we simply plug a 3 in for every x that we have, and we evaluate. So what we would be looking at here, of course, 3 squared is 9. 2 times 3 is 6. Oops. That's supposed to be a 2 still. So we end up with 18 plus 6 minus 2. So 24 minus 2. So f of 3 is 22. That's the answer we're looking for. And here we're looking at solving the system by either using substitution or elimination. I would say substitution is pretty well set and ready to go here. The first equation says x is -29 plus 4y, so we'll replace the x in the second equation with that. So we've got our negative 4, and then instead of x we have negative 29 plus 4y, and then we go back to our second equation there, minus 5y equals negative 31. So we have a bit of work in order to figure out what y is, and once we find y we'll use that to find x. So we distribute our negative 4, we get 116 minus, really, the 16y minus 5y equals negative 31. We can combine our y's. So we get 116 minus 21y equals negative 31. We'll then subtract 116 from both sides of that equation. We get negative 21y equals negative 147. And so all we have to do then is to divide the negative 147 by 21 to find y. And when we do that, we find out that y equals 7. Once we know that y is equal to 7, we can take that value, plug it back into either of these equations. I would do the top one since it's already solved for x. And we get x equals negative 29 plus 4 times 7. So x equals negative 29 plus 28. And we find out that x equals negative 1. Again, you can write that as an ordered pair, negative 1, 7. And that's the solution we're looking for. It's a good idea also to take the time to double check, plug that answer into the original system, make sure that it works. Alright, so looking at number 7 here, the way the equations line up, I would say good idea to use elimination. I would probably multiply this top equation by negative 7. So I'm going to kind of cheat a little bit with my notation here and just say multiplying that entire top equation by negative 7. When I do that, I get negative 7x minus 7y equals negative 49. And then second equation, just leaving that alone, 7x plus 7y equals 49. So I'm ready to add those together, but everything cancels out. Notice the x's cancel out, the y's cancel out, so I have nothing on the left. The negative 49 and 49 cancel out, so I have nothing on the right. So all the variables are gone. I end up with a true statement. That means these are dependent equations. So there's infinitely many solutions, but I need to describe those. And so I start by saying that the solutions are going to be an ordered pair x and y, such that, and we just pick one of the two equations. The simpler one is what we want to go with. So I got x plus y equals 7 is the equation we would use. And so this is really the way that we describe our solution set. We say our solution set is the set of ordered pairs x and y, such that x plus y equals 7. That's how we describe all those answers. Okay. Looking at number 8, we have, again, another system that looks like it's well set up for elimination. I would take and just multiply this bottom equation by negative 2. That will give me a negative 8x to go along with the 8x that we have on top. So, just writing down that top equation, 8x minus 7y equals negative 95. And we get negative 8x plus 10y equals 121. So the x's cancel when we add those together. The y's, we end up with 3y. And we get a total of 26. When we add the 121 to the negative 95. It's my mistake, except this is 122, and so then this is 27. So, dividing by the 3, we find out that y is 9. Once we figure out that y is 9, we can plug that back into either of these original two equations to find x. I don't think it'll be too big of a difference, but I'll go ahead and use the second one. So 4x minus 5 times 9 equals negative 61. So you get 4x minus 45 equals negative 61. Add the 45 to both sides, I get 4x equals negative 16. Works well. When I divide by the 4, I get x equals negative 4. So as an ordered pair, my solution is negative 4, 9. This is another system where I would recommend using the elimination method. I would take and multiply the top equation by a negative 3. That will leave me with negative 6x plus 9y equals 6. So that should start to help you see something here. So we end up with 6x minus 9y equals 6. Now, again, double check to make sure you found your products correctly. Again, the two negatives together is a positive 6. Sometimes people want to force those to eliminate, especially when they match. But really, the x's cancel, the y's cancel, so we have nothing on the left. Again, the 6's don't cancel, they actually make 12. So 0, of course, does not equal 12. So the answer for this one is that they are an inconsistent system. Solution for that is no solution, so I use the empty set symbol. Here's another system that's set up for the substitution method. So I would go with that and use the 9 minus 4y, plug that in for the x here. So we get negative 5 multiplied by the 9 minus 4y plus 3y equals 24. All I have to do then is distribute my negative 5. I end up with negative 45 plus 20y plus 3y equals 24. If I combine my y's, I get 23. I can go ahead and add my 45. So I get 23y on the left equal to 69 on the right. All I have to do is divide by 23, and I find out that y is 3. Now that I know y is 3, I can plug that back in to this first equation, plug that in for y. So if I do that over here, x equals 9 minus 4 times 3, x equals 9 minus 12, x equals negative 3. So the ordered pair that we would be looking at there, negative 3, 3. Thank you, and I hope that helped.